the second day. Remember, this is where we left off, almost. We talked about row hammer. Can you hear me in the back? Okay, I think we're going to have the same problem as yesterday, so hopefully we'll try to get rid of that fluffy noise as much as possible. So we said that main memory needs intelligent controllers, and we were going to talk more about security, reliability, and safety, and that's interaction, especially with respect to memory. But before I move on, I want to give you some thoughts on row hammer. We covered a lot of this, actually. There's a lot more research going on in row hammer. Actually, there was a paper that was just published in OSDI that looks at some software mitigations for row hammer. OSDI is happening right now, actually. If you're interested in that, you can look at that paper. That's also from the Vrije University in Amsterdam. Basically, it's a simple hardware failure mechanism that can create a widespread system security vulnerability. And how to exploit and fix the vulnerability requires a strong understanding across the transformation layers. And I like that Google Project Zero blog post a lot because it's a beautiful example of security engineering and a strong understanding of the tools available to you. I think fixing needs to happen, as I don't want to explicitly mention it over here. Fixing needs to happen for two types of chips, existing chips already in the field. These, basically, we have only control on the memory controllers that exist. If we can patch the memory controller, that's good. And future chips, I think we can have much better solutions. If you have a more intelligent memory controller that can target its solutions to row hammer, as we discussed extensively yesterday, we can do much better. Here I'll take mechanisms for fixing are different between the two types, obviously. I'll take a very quick aside. How many of you know about Byzantine failures here? Distributed systems? Okay, not a lot. So I recommend that you read it because I'm not going to cover it in detail over here. Basically, row hammer type of failures are actually a classic example of Byzantine failures, in my opinion. Actually, I borrowed this slide from Satya at CMU, who gives this course on distributed systems. And he gives row hammer as one of the three examples of Byzantine failures that happen in real life in a widespread manner. So these failures are characterized by essentially undetected erroneous computation. It's opposite of fail fast. If you have an error, ideally you would like to fail fast so that you can, you know that you have an error. Or you get no result, basically. That's a fundamental principle of reliability also. You get no result or you have an error. Now, the interesting thing is erroneous can be malicious also. The only difference is the intent. If you intend to be malicious, you can exploit a failure like this to be malicious, basically. So it's very difficult to detect and confine the sort of Byzantine failures. It's actually very, very costly, and Lamport's original paper, which I'm going to reference over here, showed that you need extensive resources to be able to do that. And if you're really interested in the theory, I would recommend this paper to think about. Basically, you need to do all you can to avoid them. That's why I think row hammer needs to be solved, and we need to do all we can to avoid this sort of failure. We cannot let it escape into the field. Okay. Any questions? I think that finishes up the row hammer part for me. Now we can talk about some future memory reliability and security challenges. So there's a lot to talk about here. As I said, DRAM is becoming less reliable, which means that it's becoming more vulnerable. If you get this sort of erroneous computation, like erroneous storage, then you will be more prone to this sort of Byzantine failures. And I've already showed this paper many times, so I'm not going to do that again. But we've also been doing studies on flash memory, and if you're interested in flash memory, this is a large-scale study of flash memory failures in the field. Again, pretty much all of the SSDs and Facebook server fleet, and there are a lot of interesting results here. Okay, basically due to difficulties in DRAM scaling, other problems may also appear, or they may also be going unnoticed at this time. We don't know fully. Some of the errors that we've seen in Facebook's fleet are interesting. They could be retention errors, but it's very hard to tell. Some errors may be already slipping into the field. Clearly, read disturb errors have already slipped into the field, but retention errors may be slipping into the field, read errors, write errors, who knows what else, right? I'm going to talk about retention errors because I think that's going to be very important. These errors can also pose security vulnerabilities, as we've seen with row hammer. So let's jump into retention errors a little bit. We talked about retention a little bit, but we're going to talk more. So the key problem is determining the data retention time of a DRAM cell or a row is getting more difficult. over time. As a result, these may be slipping into the field. And we've done this study. I'm going to tell the story a little bit backwards because this is a study that we've done experimentally after we proposed an idea. And we figured out that the idea doesn't necessarily work in real life. But basically, we built this experimental platform that I showed you yesterday, FPGA-based platform for testing memory controllers to study the retention failures, essentially, understand the data retention of DRAM cells. And basically, we've shown, actually this was well known, but we've shown that these properties are becoming much worse in the field today. And what are these two things? There are two challenges to retention time profiling. One is data pattern dependence of retention time. We've seen that yesterday with Rowhammer, right? The data patterns that cause a lot of coupling between the cells actually lead to an order of magnitude more errors compared to data patterns that do not cause a lot of coupling. That's true for retention also. Basically, the retention, I'm going to go to this next one later, but retention time of a DRAM cell depends on the value of the cell and the values of the cells that are around it, that are nearby it. And this is because of coupling. There are multiple reasons. There's word line to word line and word line to bit line coupling. Basically, when a row is activated, you perturb all of the bit lines simultaneously. This is what we've seen before. You have the word lines over here. You have the bit lines. And when you activate one of the rows over here, you perturb all of the bit lines that are connected to that word line. Okay. Okay, there you go. It's moving. Oh, it's moving very slowly. Yeah, this is the, now I have to use HDMI because what happened was I lost my connector, VGA connector. So if somebody has a VGA connector, I can borrow it. But I know that HDMI is not very reliable on my computer or for whatever reason. Okay, let's go back. So electrical noise on the bit line, whenever you perturb all of these bit lines, the electrical noise that you have on the bit line affects the reliable sensing of a DRAM cell. Let's say this is the DRAM cell in question. And the magnitude of this noise that happens on the bit line is actually affected by the nearby cells over here. Because of bit line to bit line coupling, if I can animate this, okay, that's good. You have electrical coupling between these adjacent bit lines that is affecting this bit line. Essentially, there is voltage noise. And you have bit line to word line coupling. There is electrical coupling between each bit line and the activated word line over here. As a result of this noise, the retention time of a cell depends on data patterns stored in nearby cells, because that noise depends on what values are stored in nearby cells. Which means that the implication is that you need to find the worst data pattern to find the worst case retention time of a given cell. And that pattern happens to be location dependent. That there's no single worst data pattern across an entire DRAM chip or across an entire DRAM generation. Even within the DRAM chip, you have different worst case data patterns. So this is not easy, I think. Okay. The second one is, so this is not easy, but I think this is easier than the second one. The second one is actually harder, which is the variable retention time phenomenon. Yes?
Just a quick question. Is it location dependent truly because of the location or because of manufacturing variability?
I think because of both, probably. Because of both the architecture of the DRAM as well as the manufacturing variability. Yeah. The second one is the variable retention time phenomenon. It's a bit harder. It's actually, basically, it's a random process. The retention time of a DRAM cell changes randomly over time. This was discovered more than 30 years ago by Yeni. It was first reported by Yeni in IEDM in 1987. Basically, a cell alternates between multiple retention time states. If you test it right now, it can retain data for hundreds of seconds. If you test it an hour later, it can retain data maybe less than 8 milliseconds. Right. Now, that's a problem. Well, why does this happen? Basically, I call this quantum-like effects because these are really increasing as you reduce the size of the circuit to very small dimensions. Basically, what happens is you have the leakage current of the cell. It changes sporadically due to a charge trap. Charge gets trapped in this gate oxide of the DRAM cell access transistor, and this happens randomly. And when this happens, that trap becomes occupied, the charge leaks more readily from the transistor's drain, and that leads to a short retention time. You very quickly drain, yes.
What about retention? I mean, you are still refreshing, like normally, right?
Yes, you could be, but...
or you mean retention without refresh?
Yeah, this is, just think about how long does a cell retain data without refresh?
Oh.
Yeah. Exactly. You would refresh it, but you may actually retain data less than your refresh rate.
Right.
Yeah. Okay, so this is called trap-assisted gate-induced drain leakage. And this is becoming worse. I'll show you some data related to this. And this process appears to be a random process. There are many results that show that this is a memoryless random process. So it's very hard to predict this, as far as I can understand. Basically, the key takeaway is worst case retention time of a cell depends on a random process. And you want to find the worst case retention time despite this so that you don't lose data, so that you can refresh it. So how do you do that? Not so easy. Say it again? Monte Carlo. Okay, yeah, actually, people try to model it with some Monte Carlo simulations, and it's not clear. We'll see.
ECC will help here or
So
no?
exactly. So this is a random error occurrence. So ECC is a very good solution for this. In fact,
I remember in the past there was something that attacked several bits on this,
I
like
see.
adjacent bit.
Yeah, so that's a very good question. Is it really spatial? No, actually, this turns out to be, according to our results, it's more randomly distributed.
But it is still a transient error, so I mean, SCC should take good care of it.
It's maybe, yeah, it is transient for some time, yes. So ECC actually is a very good solution for this type of problem because you don't know the error mechanism, and ECC is actually being employed in existing DRAM chips going forward. One of the big reasons is, I believe, this one, and we're going to get back to that paper that talked about variable retention time from SEM.
Cosmic rays and all this stuff. And
So, okay, that's a different one.
optic hairs, and that's also ECC.
That's right. So that's also a random process. You're talking about soft errors, transient errors that are not necessarily retention errors because of particle strikes or whatever. So that's also good to solve with ECC, yes. But this is also a random process. As a result, this is not bad to solve with ECC. But I'm going to get back to that paper from Samsung and Intel that talks about VRT as one of the big scaling challenges. Okay, so we actually, with the infrastructure that we developed, it took us about 1.5 years to develop that FPGA-based memory controller. And the first thing that we did was actually to look at the retention time issues. And this is just one example. It's the retention time of different DRAMs from 5 different manufacturers are collected at 45 degrees Celsius. So you see that the retention times are relatively large, right? Seconds, because retention time has an exponential dependence with temperature. As you reduce the temperature, retention time increases exponentially. So you see that basically newer device families have more weak cells than older ones. This is likely a result of technology scaling. So let's take a look at this. So this is manufacturer D. It's an older device family. The retention time curve looks like this. So this is retention time on the x-axis, and the fraction of cells with the retention time less than the x value on the y-axis. So this is here. The newer generation of the same manufacturer, the curve shifts to the left, meaning that you have more cells failing at a given retention time on the left. That's true for pretty much all the manufacturers. Older generation, retention time curve is to the right. Newer generation, retention time curve keeps shifting to the left, meaning that you have more cells failing again at a lower retention time. Yes? So we haven't tested 3D. This is all DDR3 chips, actually. This is data from 2012, 2013. It's good to look at those also. Exactly. Yeah. Thermally, the temperatures are even higher. Here, we fix the temperature to 45 degrees Celsius. So it's actually a relatively low temperature. That's why you see very long retention times. Yeah, it's very. But we'll get back to the temperature issue, actually. Temperature is sometimes low. Okay, so this is an example of VRT cell. This is real data from one of the manufacturers. Basically, this is time of testing the retention time. And it's over hours. It's about 11 hours, as you can see over here. And we see different retention times. And this is capped at 6.1 seconds because that's the maximum time we test for retention time. But sometimes you see that the retention time goes down to 3 seconds. Sometimes it's somewhere in between. Sometimes it doesn't fail, basically. It's 6.1 seconds. So you see this jump between states. And this is classic variable retention time cell. You don't have a single retention time. OK, so this is a chip. We wanted to look at the population of these cells in one of the more recent chips at that time. So if you don't, what this figure is plotting is minimum retention time of the cell on the x-axis and the maximum retention time of the cell on the y-axis. And it's a density plot. The darker colors means there are more cells that are at that point, at that xy point. And if there was no variable retention time phenomenon, you would expect all of the cells to fall in the XY curve, right? Basically, this is expected if there's no VRT. Minimum retention time should be equal to the maximum retention time. Of course, there would be heterogeneity across the cells, so some cells would have lower retention times, some cells would have higher retention times over here. And again, this is capped at 6.1 because that's the longest we test. But most of the cells actually exhibit variable retention time, as you can see. Actually, a lot of them are over here, meaning that many failing cells jump from very high retention time, which is the maximum retention time over here. They don't fail over here. But the minimum retention time is actually very low for them, which means that this phenomenon is actually affecting many, many cells. And this paper has a lot more detailed results on this. OK, this is just one example. And this is becoming worse. As technology scales down, we're seeing more and more cells falling around here, and fewer cells that have minimum retention time, same as maximum retention time. Which means that testing for the worst case retention time, ideally you would like to find the minimum retention time of a cell, right? Testing for this one is becoming much more difficult over time. Actually, something that I didn't include over here is how what is the time scale at which a cell switches between one retention time and another retention time. It turns out it could be days or hours. So you need to test for days or hours to find the minimum retention time if you ever get to it.
So
yes?
If the minimum is 1 second, why do we refresh it every 64?
So again, this is collected at 45 degrees Celsius. Refresh rates are exponential. Yeah, actually, the paper has a lot of data. This paper has a lot of data. It fits a nice curve, basically. And other people have shown this also. It's refresh interval exponentially, retention time exponentially reduces with increased temperature. I don't remember the equation. OK. But you can relatively easily predict it. So this is exactly the reason Samsung and Intel, when they wrote the paper in 2014, basically said VRT is one of the biggest scaling challenges of the DRAM process. It's occurring more frequently with cell capacitance decreasing, so you have a problem. And the solution that they proposed in this paper was actually adding error-correcting codes inside the DRAM chip, which is what's happening in the field right now. Because it's very difficult to, I think, solve this problem without adding error-correcting codes. If someone comes up with a method of discovering these variable retention time cells, I think that would be groundbreaking. OK. Actually, I think it's interesting to see that error-correcting codes are being added inside the DRAM chip today, because in my opinion, if you went to a DRAM manufacturer 10 years ago and told them, I want error-correcting codes inside your DRAM chip, they would kick you out of the room because they don't want to get rid of their capacity. If you add error-correcting codes, you're getting rid of some natural capacity inside the DRAM chip. And in existing DRAM chips, you basically lose about 6.25% of the capacity. So they don't actually disclose what it is exactly, but we have some thoughts on what it could be.
Oh, it's
yeah, that's another issue, I think, currently. Currently, the DRAM chip corrects the errors internally, but memory controller has no idea of this. So those don't get exposed. Yeah, yeah. That's right, yes. Yeah, something less. Yeah, exactly.
And there's no 9th bank. It's still 8 banks.
So, yeah, all of that information is not disclosed. Okay. It happens internally. I think in the future, it's better to have this information exposed to the memory controller, but yeah, so that you can take some action, right? But I'm not sure if maybe the Intel folks can correct me over here if I'm saying something wrong. Yeah. Okay. Okay. So this. Yeah, we can talk about basically how the error correction should be structured. But let's go back to refresh. So why is refresh a scaling problem? This paper also said that refresh is a scaling challenge. As we said, refresh and VRT, actually, they said these two things are different. Even though they're related, clearly they're different. So refresh is actually, in my opinion, still one of the biggest challenges in DRAM, and it should be solved. So when we wrote this earlier paper, we were a bit more naive. I'm going to tell you the story of it. Basically, this is what we projected at the time. This is from ISCA 2012. Basically, this is the percentage of time the DRAM chip spends refreshing. And this is the chip of the time. Basically, the throughput loss due to refresh. You cannot access the device because the device has to refresh. It was about 8% for a 4 gigabit chip over there. And we projected that, maybe a bit aggressively, that if you actually designed a 64 gigabit chip that's much bigger. You add more rows, and also technology scales to much smaller technology nodes. You have 64 gigabits in a single chip. This chip would spend almost 50% of its time refreshing, losing throughput. Yes?
Can't you, through a small circuit change, be able to refresh in parallel? Like segment the bit line so that you can refresh rows
Mm-hmm.
in parallel.
Yeah.
It'll cost you the energy, but at least not the access time.
Yeah, some of those tricks may already be employed internally in the DRAM chips. But yeah, I think better refresh architectures are still needed. Like we've discussed yesterday, if you could refresh one subarray while you're accessing another subarray, right? I think some of those tricks are employed to do refresh internally in parallel. Okay, but still, it's consuming a lot of energy, a lot of throughput, and in the future it's expected to consume more. We've actually corrected some of these projections. Our paper from HPCA 2014 shows two scaling trends. One goes up to 40% or so, and the other one goes up to 25% or so. But still, 25%, 45%, these are big numbers if you want a big chip. And the reason refresh increases because you add more rows, you have more rows to refresh, and technology scales down as well. As a result, you need to do refresh more. And this is the energy overhead. You can argue with these numbers even more because this assumes some activity factor, as you can see. With some assumption of activity factor, this is the percentage of DRAM energy spent refreshing. It's about 15%. And we expected that it would go up to about 40, 50% if you actually had a much larger chip. So the key realization is that most refreshes are actually unnecessary. You don't need to be on this curve at all. If you look at the retention time of DRAM, as we discussed yesterday, it looks like this. And if you know this retention time reliably, and if you expose it to the memory controller, expose it to the operating system or software, somehow you ensure that either you don't use these cells or you refresh them more frequently compared to these other cells. That way you can actually get rid of a lot of your refreshes. And what we proposed...
Or maybe you can do something like wear leveling in existing memories. Just make sure that those addresses are kept busy.
Yeah, you could do that. Basically, they're not used.
Well, actually, the other way around. To use them more frequently, so you wouldn't have to...
Oh, I see. Yeah, exactly.
Anti-wear leveling.
Exactly. If you know the retention time of different rows, and if you can expose them to, for example, maybe software, then maybe you can allocate structures such that their lifetime doesn't exceed the retention time of the rows, and then you naturally don't need to refresh. If you have that sort of predictability and determinism in the system, I think there are a lot of tricks that you can play. But one solution could be not using those cells also, right? That may be an easy solution. Okay, so what we proposed at the time was, okay, we first need to, regardless of whatever we employ, we need to reliably figure out the retention time of all DRAM rows. And this is the Achilles heel of all of these mechanisms. We need to somehow profile. And at that time, we were naive. We said, okay, you could profile easily. But this is that's exactly why we built the infrastructure that we built to figure out whether we could actually really do that. Okay, well, assuming you know this profile, the idea is you store this profile into bins by retention time. Basically, store rows into bins by retention time. For example, you just need to have actually, ignore this 128. Assume that this is 64 to 256. Basically, that's the retention time of the cells. You can have a single bin storing which rows need to be refreshed every 64 milliseconds. And you can refresh everything else every 256 milliseconds. Then the question is, how do you actually construct that bin? Basically, we use Bloom filters to have scalable storage for this. So Bloom filters are good because if you insert a row into a Bloom filter saying that it needs to be refreshed often, you get false positives sometimes because Bloom filters are an approximate representation of set membership. How many of you know about Bloom filters? I'm talking about this, but okay. How many of you don't know about Bloom filters? Okay, that's a majority. Maybe we should cover Bloom filters. So basically, Bloom filter, okay, I'll have to do this, I think. Otherwise, it's not going to be fun. And this is such a fundamental concept, I think that we should cover this. So basically, assume that you have some number of rows in memory. And this is all of your rows. I don't know, 2 to the 64. I'm going to make it up very high. And basically, needs, I'll call this need frequent refresh. So what we're trying to do is, we know that we figured out the retention time of all rows. We want to mark those that need frequent refresh every 64 milliseconds. One way of doing this is for every row you have a single bit, right? And you basically set the bits for those that need frequent refresh, which is going to be based on this distribution that I showed you, very few rows. So this is exact set membership representation, right? It's a bit vector, basically, and you have a single bit for every possible element in the set. And it's very costly, 2 to the 64 bits, basically. So a Bloom filter, which was introduced in 1970 by Bloom, says there are certain problems where you don't need this exact representation. And if you have one of those problems at hand, you use an approximate representation. And the idea is, very simply, don't have a bit vector that covers every single element. Have a much smaller bit vector. Let's say 1,000 elements, 1,000 bits. Much smaller than 2 to the 64, as you can see. And for those rows that you know needs to be refreshed frequently, insert their addresses. So let's say row 1. What you do is you set a bit that corresponds to row 1. Now, what bit corresponds to row 1? That could be, yes, that could be one way. But it turns out if you want to make this nicely utilized, you go through a hash function. You take the address. In the general case, I will say that you take the address of the row that you want to insert into the Bloom filter. You go through a hash function, and you set a bit. And then let's say you want to insert row 3. Again, you take the address, go through the hash function, and set another bit. And then let's say you want to insert row 5, blah, blah. You keep inserting these bits. In the end, you've inserted all of those rows that need to be refreshed every 64 milliseconds into your Bloom filter. And if your Bloom filter is larger than the number of rows, then you don't have all of the bits set. That's great. Now you've represented this, right? It's not an exact representation because some of the addresses actually, because you go through this hash function, because you don't have enough bits to represent all possible addresses, some of them conflict. So when you set this bit, some other row address will also set that bit, perhaps. So they conflict naturally, right? Because you have too small number of bits. Which means that when you actually need to query whether a node needs to be refreshed frequently, you take the address, you go through the same hash function, and you check whether that bit is set or not, right? For each address, yeah. So when you're in the memory controller, basically when you're trying to do refresh, you go through every single address, and you check whether it needs to be refreshed or not. And this Bloom filter, small Bloom filter, will tell you if the bit is set for that particular address, it'll tell you, OK, refresh it frequently. Otherwise, don't refresh it frequently. Now, the good thing is this is small. And it gives you always the correct answer, because if you actually ever set a bit, you're going to get the answer that, oh, you should refresh it frequently. You won't do something wrong. But you will get false positives, meaning there will be some addresses for which you will get refresh frequently, even though you never inserted that address over here, because those bits alias with whatever something else that you inserted over here. Yes?
Why does it make sense to use that hash function in DRAM? Because you said that the rows that need frequent refreshing are place dependent. So does it make sense that there are a place in the DRAM that needs more refreshing, and there's a place where you don't need? So on the contrary, you will want to make these remove the hash function just by scope of address.
Yeah.
Like row 0 to 10 will be together, because if they need refresh, any one of them, it makes sense to make all of them refresh frequently.
Why is that? Because
If you pass them through the hash function, then you'll get more bits set on that small array.
I didn't understand that, because this hash function is just to distribute as opposed to taking, let's assume that this is your physical address. As opposed to taking some bits, you go through this hash function so that you can distribute the
That's what I'm saying.
ones.
Why you want this to distribute? If you're saying that the refresh rate is dependent on placement of the rows, you don't want to distribute. You want to keep them
I'm not getting you, I think, because what we're trying to do is insert the addresses that need to be refreshed often, right? So this is not this bit vector has nothing to do with the layout of the address in memory. It basically just tells us, oh, given an address, should we refresh it more frequently or not? Uh-huh. It could be random, yeah. Yeah, it's random actually.
Why is it random if you say that the refresh rate is dependent on placement? Isn't it?
So I didn't say that refresh rate is dependent on placement. It's this is so I think we have a disconnect here. So basically, this is just showing the distribution. Yeah. Okay, maybe. So basically, this actually can be distributed in any way. There could be clusters, sure, but it's not guaranteed to be that way. And according to our results, actually, the weak rows are distributed all across the DRAM in a more or less random manner. And this is just a trick to actually make this storage much more compact.
So the point of Bloom filter, you have false positives, but you never have false negatives.
Exactly. Yeah, basically you have false positives, so you refresh a little bit more frequently because some of the addresses that you didn't insert here will be, the Bloom filter will tell you that actually you have inserted, but that's wrong. But that's okay, you refresh some addresses more frequently. But you never have false negatives in this because whatever you inserted over here, you will find it the next time you query the Bloom filter. And now you've reduced the requirements of your storage significantly.
What is the percent of the small section?
Okay, I'll give you, it's very, very small, actually. So basically, it's about 1,000 rows in a 32 gigabyte DRAM. It's not a lot.
So why can't you just take a few bits or make a simple hash function out of it?
Why don't you get rid of this?
No. Just the hash function instead of talking about Bloom filter and you take hash function. But can't you just take a few bits out of the address and use that and that's it?
Yeah, you could take a few bits. That's right. So the hash function is basically just to distribute you better utilize the bit vector. So actually, in the paper, you see that this hash function is important because it affects your false positive rate. So how your ones are distributed over here affects your false positive rate significantly. Yes.
For example, if you have 1,000 rows that need this addressing and your array is 1,000 rows, with a good hash function, you fill all of it.
That's right. So you don't have 1,000. I just made it up. So you need something bigger. But what happens is actually usually in Bloom filters, I didn't tell you this, but you really want more confidence. A single bit, the probability of conflict on a single bit is very high. So how Bloom filters are usually designed is you have hash function 1, hash function 2, hash function 3. You take the same address, you go through all of them, and these all generate different bits. And all of the bits need to match for a Bloom filter to declare that something is inserted into it. So that builds more confidence. I would definitely recommend folks to read the 1970 paper by Bloom because it covers a lot of these issues, and people have actually perfected the design of Bloom filters over time. Yes?
You compare the energy cost of the controller work to the energy cost of refreshing, the refreshing and saving?
Yeah, we have it in the paper. Yeah. Okay. Okay, so hopefully now it's clear. So let me pull back. The takeaway is this is an approximate representation of set membership, and we're trying to represent the set of rows that need to be refreshed often. And we're using this structure over here. So you could also say, well, why aren't we using this? Because this is expensive. Why aren't we using a simple table? You could say that. That's a separate thing, right? That's different from this structure. You could use a simple table that has basically 1,000 rows. But that's expensive. Now it's more content addressable memory. And also it has one issue. If you add more memory into your system, you need to increase the size of the table, or you need to provision the size of your table such that it would keep the maximum number of rows that have to be refreshed frequently. Whereas the Bloom filter you could keep inserting entries. In the worst case, your false positive rate increases. In the worst case, your false positive rate becomes 100%, and you're no better, you're no worse off other than the energy you spent going through the Bloom filter, right? Okay, so that's why this is more scalable storage. Okay, so basically, the storage that we have in the controller is only 1.25 kilobytes for a 32 gigabyte DRAM memory, and you can read the paper for more detail. So now that you store this in the, by the way, this is a hardware, we use this as a hardware structure, but this is a software structure also, right? You could use Bloom filters for many purposes when you're writing programs, assuming your problem can tolerate false positives and you want no false negatives. Okay, so now that we have this structure inside the memory controller, what does a memory controller do? Basically, memory controller refreshes rows in different bins at different rates. It probes the Bloom filters to determine the refresh rate of a row. And that's easy to do. The paper has more detail. And the key takeaway is you can reduce refreshes by approximately 75% because of this distribution. And you can reduce energy consumption and improve performance. So let's talk about how to implement this very briefly, and then we'll get to exact performance numbers. So you could actually do this in existing systems. A refresh control is in DRAM, auto refresh systems. Radar can be implemented in either the controller or the DRAM. It has different implications on the interface. If you actually put it in the controller, so when we proposed, we actually had 2 Bloom filters, as you can see over here. The overhead is small. You have about 3 counters. And you need additional commands for per row refresh, because every single row, you need to decide whether or not you refresh. You refresh very few number of rows, but the refresh is under the control of the memory controller right now. And this is all accounted for in the evaluations as you asked. You could also put it into DRAM. Basically, if DRAM manufacturer somehow figures out the retention time of rows, DRAM manufacturer can embed a radar-like mechanism inside the DRAM. And whenever the memory controller issues a refresh command, the DRAM itself figures out what to refresh and what not to refresh. And the overhead is like this. But this may require some change to the interface if you want to really take advantage of this. Yes?
So, if you just lower your refresh rate for the 256 milliseconds, and for the rest of them, when the controller is doing it, you just activate pre-charge, then you don't need to change the interface.
Exactly. I agree with you. I agree with you. I like that solution much more. Your default refresh rate is 256 milliseconds, and you compensate for the additional things. But then the control is still in the memory controller, right? It's not this solution. Yes. I like the memory controller solution better, actually, for not only the reason that you suggest. There's another reason. You could say that, oh, this is doable. But it turns out this is not very realistic. You can, because the DRAM manufacturer doesn't really know the retention time of its cells. Why? DRAM manufacturer may test a DRAM chip after it's manufactured and figure out the retention time of the DRAM cells. Of course, all of the other things that we discussed apply, data pattern dependence and variable retention time. But once that chip gets soldered on a DIMM, it gets exposed to very high temperatures, let's say 300 degrees Celsius. And that changes the retention time profile of the cells. And that leads to a problem. The DRAM manufacturer's profile may be completely incorrect at that point in time.
If you're doing the profiling later on, you can still program the DRAM.
That's true, yes, assuming you have that mechanism, right? So after doing the soldering on your DIMM, you need to go back to the chips and put the profile inside, right?
What if the temperature changes within the operation? Then the tables have to be changed.
Yeah, so you need to, in this case, you need to find the worst case retention time at worst case temperature. Yes. Of course, you can be more fancy and you can have different radars for different temperature levels, but that increases the overhead. Yeah, these are very good questions. Okay, so let's take a look at the results. We simulated this, of course. The hardware cost is relatively small in the memory controller, and the refresh reduction is about 74.6%. It's not exactly 75% because there are some rows that need to be refreshed more often, and there are false positives as well. And actually, the paper describes an exploration of the design space exploration for the Bloom filter designs for this. We found that dynamic DRAM energy reduction is about 16%, and idle DRAM power reduction is about 20%. And the performance improvement is also significant because you're getting rid of refreshes, which means that you're actually enabling DRAM to be accessed by demand accesses. And benefits actually increase as DRAM scales in density. I like these graphs. You could argue with the trend scaling, of course, over here, but this is the energy per access on the y-axis. Actually, I may have a better one over here. Let me see. This one. I'll start with this one. So this is the energy per access. This is the basic existing mechanism, auto refresh. As you can see, with device capacity, energy per access is increasing. If you employ radar, you save energy at all device capacities, and the savings are much higher at 64 gigabit device capacities. Ideally, if you really want good scaling of memory, you want energy per access to remain constant over generations. But as you can see, even with radar, we're not remaining constant. So you actually need more solutions than radar to scale well into future generations. And this is the performance improvement. As you can see, the performance improvement is much higher if you have much larger devices. Of course, these depend on scaling assumptions that we made. That's why the performance improvement is huge if you have a 64 gigabit device, because as I showed you earlier, the 64 gigabit device is spending about 46% of its time just refreshing and doing nothing else. And if you get rid of most of the refreshes, then you actually enable access to that device for a good chunk of that 46% of the time. So this is a good solution scaling into the future, I think. The key issue is, of course, how do you profile the retention times? Okay, so this is one slide summary of radar. Okay, so let's talk about this profiling a little bit more, because remember, the history is we proposed this idea, and actually this is some data from Samsung's earlier paper in Electron Design Letters in 2009, and we actually wanted to verify this with our own infrastructure, and that's why we built that infrastructure. And it turns out this profiling is the hardest part of this. I think you can do all of this, but figuring out the retention time is not the easy part. And that's the radar paper. You can take a look at. So the key question is, how can we reliably find the retention time of all DRAM cells so that we can make DRAM reliable and secure, and also we can make techniques like radar work? Because I think there's a lot of potential for this to improve performance and energy. And we did a bunch of studies later on looking at the issues. How do we actually mitigate these retention failures in DRAM? How can we discover them? And what are the different techniques for doing them? I'll give you the basic ideas. But basically, the thing that I'm going to describe is online profiling. It's very difficult to have a static profile of retention time and say, oh, this is the retention time of all my cells, and it's not going to change anytime into the future. You really need to do this profiling periodically once in a while the system is in operation because of issues like VRT and DPD, because the data pattern depends. You may not really know exactly what's the worst case data pattern. And also there are other issues like aging and wear out we didn't even examine over here. Basically, there are several key observations. One is testing alone. If you keep testing, you cannot detect all of the possible failures. Meaning that there are some variable retention time type failures, or maybe there are some failures that are dependent on the data pattern that keep appearing as you keep testing. So basically, you get about one error every hour after you test for days. And maybe your error rate reduces, but you keep getting errors over time. Basically, you need to combine testing with ECC, error correcting codes. There's no other solution from my perspective so far. If you don't have ECC, you cannot really figure out the retention time of all DRAM rows effectively. And we found that, of course, having ECC and other mitigation techniques degrades performance, because testing, if you do online testing, if you want to profile the retention time of cells, you need to take off part of your DRAM. You cannot access it. You need to profile the retention time. It takes a while, right? So testing can help reduce ECC strength, even when starting with a higher strength ECC. So if you're interested, you can take a look at this paper. Pictorially, this is what it looks like. While the system is running, you protect the rows with ECC initially. And you periodically test parts of DRAM over time, and you figure out the retention times. If you're not getting errors at a low refresh interval, then you say, oh, ECC is too strong, so I'm going to reduce the ECC for those rows that seem to be doing well. Of course, you don't get rid of all of the ECC from those rows, because if you get rid of it, you may actually get an error with the reduced refresh rate. You have some amount of ECC that's always there for the profiling. That's the idea. And you run tests periodically after a short interval at smaller regions of memory to reduce the profiling overhead. If you want more details, it's in the paper. And I think this is the most recent work. And this basically does essentially what I described. we basically want to figure out which cells have errors when you reduce the refresh rate. So you need to protect the DRAM with ECC to be able to figure out that you have errors when you reduce the refresh rate. So the insight is that you want to avoid retention failures. When you make a row, when you downgrade a row such that it's refreshed less frequently, you want to upgrade it if you get an error when you do that. And to be able to detect that error, you need error correcting codes. Now, the observation we have as rate of variable retention time errors is actually much higher than the rate of soft errors. So this is going to enable us to maybe use ECC for both of them at the same time. So we found out that the rate of variable retention time is actually more than 50x to 2500x higher than soft error rates that are observed in the field. So the basic idea is very simple. What happens is you have, assume that this is this bit vector over here. It doesn't have to be the bit vector, but it's the bit vector, let's say. And assume that you set something to 0 if it doesn't require a lot of refresh. You reduce the refresh rate for this row, and you get an error. If you get an error, then you correct the error, and then you set the bit such that the next time you refresh it more frequently. That's the idea. The row is protected from future retention failures. And it's obvious, I think, but I'm not sure if there's a solution without ECC. If someone comes up with a solution without ECC, I think that'd be great. It's a bit disappointing for me, frankly, because we didn't want any ECC here, but I'm not sure if you can do, given that there's something like variable retention time, and we don't know the worst case data patterns perfectly, we may need something like ECC. And actually, scrubbing works to our advantage. Many server systems do scrubbing of memory once in a while. Scrubbing meaning they go through the memory and they correct the errors, read and write, using ECC. And using the scrubbing mechanism, you can actually do this upgrade and downgrade of the DRAM rows. Okay, I'm going to skip this. So okay, this is what happens basically to the savings. So this is the refresh savings. If you have no variable retention time, which is what Rader assumed, your refresh savings would be constant over months because you know exactly the retention time of your rows. Assume that you know the perfect data pattern also. With Avatar, over months, you discover that some rows actually exhibit variable retention time, and you downgrade and upgrade over time. As a result, your savings reduces, as you can see over here, because you accumulate more rows into the population of those rows that actually exhibit variable retention time. But it's not that bad, as you can see, because the discovery rate of variable retention time failures is not very often, very frequent. And maybe actually you can mitigate that by adopting better strategies in terms of testing. Maybe you decide, oh, okay, after 6 months, I'm going to test the DRAM again, and then maybe you go back to this curve, and then you go down after that. Okay. And this is some more data that looks at the performance improvement that you get. It's similar in nature to whatever we showed with Rader. And it gets reasonably close to no refresh, but maybe not perfectly close. But this is 1 year. After 1 year, what happens? Of course, we didn't run it for 1 year. We did simulation based on the observed error rates that we had from our infrastructure. Basically, we get about 2/3 of the performance improvement of no refresh with this mechanism. And I think this is a realistic mechanism. And this is the energy delay product improvement that you get, again, after 1 year. Okay, any questions?
We have an argument here. So
Okay, I can see that. Yeah.
can't you have an outage, power down like every 6 months to solve this problem?
Yeah, I think so. I mean, to solve this problem, meaning,
Switch the damn thing off.
yeah, you could switch it off, and then you could profile again, and then you could start from a curve. But I think while the system is running, you need to do something, right? You cannot just ignore variable retention time if you want to optimize refresh. Okay, so there are more works actually. There are more ideas that are needed. This basically looks at detecting data-dependent failures. I'm not going to cover the data-dependent failures. This is a very hairy part of DRAM, I think, data dependence. But if you're interested, you can take a look at the paper. And this actually is an idea that exploits the memory content. If the memory content doesn't change, you don't need to profile often. And that's actually very useful. This paper shows significant benefits by that. Actually, if you know the memory content of some DRAM rows, maybe you don't even need to refresh it, right? Because you're not going to lose data with the content that you have inside there. So it's good to think about that, the content. But I'm not going to cover that. There are a lot of potential ideas. I'm going to talk about this one a little bit because I think this is a more rigorous analysis that we did last year on the most state-of-the-art chips at that time. And things have improved, of course. We have new state-of-the-art chips. Basically, we wanted to analyze this profiling because you need to do profiling once in a while, online profiling. And that is very costly. And we wanted to minimize its overhead. And we wanted to understand its trade-off space. And we wanted to enable a much faster profiling method. So we're going to talk about an idea that tries to profile DRAM at higher refresh intervals and temperatures so that you target a lower refresh interval and lower temperature. So let's go over this a little bit very quickly. Yeah. This topic is very exciting, I think. Are people interested in this? Am I the only one who's excited? Hopefully not. Okay, good. Okay. So basically, the problem is this. You have leaky cells. You need to periodically refresh it. As a result, you get performance and energy overhead. So our goal, as I said, find all retention failures for a refresh interval T that's greater than the default refresh interval. Of course, by the way, I say default refresh interval assuming that there are no errors below the default refresh interval, but we don't know, right? Maybe there are some errors that are slipping into the field because some cells are not satisfying the default refresh interval. We don't know. So basically, there are a bunch of things that lead to that make it difficult to identify this: process, voltage, temperature, aging, variable retention time, and data pattern dependence that we've discussed. So what we did in this work is actually we studied. This was the first characterization that I know of, relatively large-scale characterization of LPDDR4 chips. We studied about 368 chips, and we found that cells are more likely to fail at an increased refresh interval and increased temperature. And there's a very complex trade-off space between profiling speed, coverage, and false positives. I'm not going to go over all of this. There's a lot to talk about here. But basic idea is if you want to operate here at a refresh interval here and a temperature here, it might be a good idea to profile aggressively over here. And this is called reach profiling. If you want to reach here, you actually profile here. Meaning, what does this mean? Basically, you profile at a much higher refresh interval and much higher temperature, if you can. If you can do this online, that's even better. Of course, you can maybe do the online profiling at a higher refresh interval, but it's not clear if you increase the temperature intentionally to do the online profiling. But maybe you can. And the key realization is that you get a superset of the cells that are, you want to find the cells that are failing here at this refresh interval. If you do the profiling here, you get a superset of the cells that are failing here, which means that you naturally have some false positives because you profiled here, but that may be okay. You get a high coverage of the cells here, and you hopefully get a high accuracy, and you still get lower profiling cost because profiling here is actually hopefully faster. Okay, I think I already said this basically. So let's go over some results. I think some of these are interesting results. Basically, we characterized chips from 3 major DRAM vendors, and this was our accuracy. This is the most accurate testing chamber that we've done so far. Yeah, and you can read the paper for more details. So we've seen variable retention time is actually increasing. This is a representative chip from one vendor to 2-second refresh interval at 45 degrees Celsius. And basically, this is the number of new failing cells that you observe because you've increased the refresh interval. And this is time, days. As you can see, there's usually one cell that is failing pretty frequently, and it's very constantly. So this means that you cannot just keep testing and figuring out all the errors because you'll always get a cell failing going into the future. New failing cells continue to appear over time. And the set of failing cells changes over time also, actually. And I think this was well known before, but this error correcting codes and online profiling are necessary to manage the new failing cells. Now, we did some analysis of the distribution also. So if you look at the probability of a read failure of a given cell at different refresh intervals, if you idealize it, you would like it to be like this, right? Assume that you have a retention time of 3 seconds. The cell fails at retention times that are greater than 3 seconds. The cell operates correctly over here. But real life is not like this. Real life is actually much worse. The actual cell has a distribution that looks like this. And this is actually a real measurement from a real single cell. This is a single cell failure probability based on many testing that we've done at these refresh intervals, as you can see. And this is the read failure probability. So there's no nice curve where things are cut off. So this, for example, failed 9 times out of 16 trials over here. Okay. And these are different real cells that are tested. It's fun to look at them. And we idealize the curves a little bit. Now, the question is, if you want to operate at this refresh interval, let's say you decided this is a good refresh interval to operate, you see that there are some cells that are failing, right? These cells are failing. It's low probability, but it's a dangerous probability still, 20% of the time. So how do you figure out these cells that are failing? And these are very hard to find if you keep profiling at this refresh interval, as you can see. This is relatively low probability. So the idea of reach profiling is basically profile the cells here. What happens is now it's very easy to find these cells because most of the time they're failing over here, and these are the same set of cells. Unfortunately, you also find some of the other cells, like this one fails a lot over here, but doesn't fail at all over here. That's a false positive, basically. You say it's going to fail because you profiled here, but if you operate over here, it's not going to fail. And this one is actually, maybe you say, okay, this is going to fail over here, and you be conservative and you say, oh, it's going to fail over here also, but then you have a false positive again. That's the basic idea. Any cell is more likely to fail at a longer refresh interval or at a higher temperature. So that's the idea of reach profiling. I said this already. Profile at a longer refresh interval and or a high temperature. And it turns out this is very fast and reliable. It searches for cells where they're most likely to fail. You don't need very long profiling intervals, times. The con is false positives now. Basically, profiler may identify cells that fail under profiling conditions, but not under operating conditions. But of course, we get rid of a lot of false negatives. That's the upside. Okay, it's a general methodology. There are 3 key questions that the paper answers, which I'm not going to go into a lot of detail. What are the desirable profiling conditions? How often should the system profile? What information does the profiler need? And there's a lot in the paper. And we actually talk about 3 key profiling metrics: how long profiling takes, portion of all possible failures discovered by profiling. Ideally, you want this to be high, you want this to be low, and false positive, number of cells observed to fail during profiling, but never during actual operation. You want this to be low also. Although false positives may not be that bad because your mechanisms can tolerate it, right? If you're, for example, handling the retention time failures with some ECC, false positives can be tolerated by ECC. Okay. So we actually evaluated the results that we get from real system using performance simulators. I've described Ramulator yesterday, but we have energy models integrated into Ramulator also. I'm going to give you very quickly some results. Take this with a grain of salt. There's a lot of methodology involved here, but basically, if you do brute force profiling, it becomes very undesirable at higher refresh intervals because you're really profiling a lot of things for a really long time. Reaper becomes much better at higher refresh intervals, so you can actually push the refresh interval higher. If you have ideal profiling, actually, that's the best. Ideal profiling, actually, it doesn't consume any time, essentially. Here, you reprofile rarely. Here, you reprofile often. So you want efficient profiling mechanisms, especially in these regions over here. That's the refresh interval, higher refresh interval. So key conclusions. Reaper is a relatively, in my opinion, doable online profiling mechanism. It enables about 16% performance improvement and 36% DRAM power reduction, according to these results. Of course, take this with a grain of salt. And it turns out that it enables longer refresh intervals, which are unreasonable using some brute force profiling methods, which were proposed previously. And there are a bunch of other analyses in the paper. If you're interested in that, I'll point you to the paper. I like this part a lot, probabilistic model for, this has a mind of its own, tolerable failure rates. I think there needs to be more research in that direction. Okay. Any thoughts? Questions? Okay. I'm going to talk about this later on when we talk about latency, actually, which if we get to it today. So you can actually, by understanding the devices, this is another study that we did with LPDDR4 devices. By understanding the devices, you can actually create new functionalities by taking advantage of DRAM. In this case, for example, we reduced the latencies, and we looked at the error patterns resulting from reduced latencies, and it turns out that gives you very good signatures of the device. They're also very good random number generators. We have a paper under review related to random number generation. But these devices can be used as physical unclonable functions also. So I think that's the interesting thing that you can do by understanding the nature of these devices. You may actually reduce the refresh rate, but you can also enable new use cases for DRAM. Yes?
I'm sorry.
Yeah, sure.
Question to the last.
Okay, sure. Which one?
Previous topic. This one.
This one.
The VRT in general. So the troublemakers, the cells that exhibit this VRT behavior, they're basically staying the same. So if today I'm a troublemaker, I'm going to be a troublemaker tomorrow.
Not necessarily.
Or they're just jumping all over.
Exactly, they're jumping all over. Yeah, that's why you keep discovering new cells as you keep testing.
You are a troublemaker for
No.
until the next 6 months or something.
Not necessarily. No.
Okay.
Yeah, our results show that that's also not very easy to predict, basically.
You consider them that way.
Oh yeah, we consider them. Yeah, we consider exactly. So there could be better ways of blacklisting and whitelisting those cells. We didn't do. We were a bit conservative in our evaluations. If once you're a troublemaker, we marked you as a troublemaker for a long time. But I think you can profile once in a while and then mitigate that.
The 6 months period, sort of, when you mentioned.
Yeah. So 6 months is too long. So actually, these cells change behavior within the order of, as I showed you, some cells within the order of minutes or hours.
Yeah.
So, but to be able to figure out that whether you're a troublemaker or not. Okay, figuring out whether you're a troublemaker is easy if you have ECC. That's fine. But to whitelist a cell, you need to do profiling, and that actually has overhead. Right.
But you cannot figure out it from other, I think, other details from the analogic of the
Yeah.
manufacturer maybe can know about the charge that is.
Yeah. No, that's not easy. It's these are very small things. So I think what you're getting at is, can you somehow figure it out based on some other metric? I don't know the answer to that one. Exactly. You can.
But maybe because you need some here you use ECC because you know that is right or wrong.
That's right. Exactly.
You need some signal that.
Exactly. Yeah. Whitelisting is hard. Blacklisting is easy, right? Because once you cause an error, you can blacklist. But whitelisting is hard.
The percent of the blacklisted is small.
That's true. That's why you can still get 60% savings. Yes. Exactly. The percent is small, but it keeps increasing slowly and slowly. What do people think? Do you want a break? 5 minutes? Okay, so if people want 5 minutes. Let's do 5 minutes. It's a good natural place, actually.